cosmos, space, and time travel, science and technology. Brought to you by theoretical physicist, futurist, popularizer of science, and world-renowned author, Professor Michio Kaku.
And GCNlive.com.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, every week we profile some of the most amazing developments in science technology that touch our lives and change the way we see the universe. And speaking about the universe, perhaps the strangest object in the entire universe are black holes. That's the stuff of science fiction, you may think, but no. With us today is Professor Jana Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, and she has a new book out, Black Holes Survival Guide. So we're going to talk about whether or not you can survive a black hole. And if you want to find out more about this show, Science Fantastic, go to my website. It's mkaku.org. mkaku.org. We have 4 million fans on Facebook, and I've also written 4 New York Times bestsellers. My latest New York Times bestseller is called The Future of Humanity, Humanity in Outer Space. What happens if we go back to the moon, go on to Mars, and even beyond? What are we going to find in the deep vastness of this universe? Well, once again, with us today is Jana Levin. We're talking about her latest book, Black Holes Survival Guide. So, first question for you is, how did you, as a youth, think back to when you were a kid? What got you interested in science?
You know, it's funny. I really wasn't that kid who identified as a scientist. Although in retrospect, I had all the signs. I definitely remember staring out my window into the sky and speculating about what was out there and trying to figure out what it meant that the Earth was round. Like when I was very little, at one point I had a very failed theory of cosmology that when I heard the Earth was round, I thought it meant we were inside the globe, kind of like the Truman Show. And so I always was asking questions and theorizing about the world, but I don't know. It didn't occur to me that meant I had a scientific leaning, and now I understand that that's exactly what that is.
So what steered you in the direction of hard science and eventually, of all things, physics?
Well, I came to college, and I thought I wanted to be a philosophy major. I was interested in the big questions. I was always kind of reveling in the big questions and the unanswerables. And it took me by just studying the curriculum and in college to realize, actually the way to answer these questions, no knock to philosophy, is really through physics. And I became completely enamored of physics very suddenly and completely unexpectedly. And the math I actually very much like. I really enjoy doing math. And I think I was so kind of insecure because I came to the subject so late. And so here I'm studying physics, and all of my peers had been doing this since they were kids. They always knew that that's what they wanted to do, and so I felt incredibly behind. I didn't know even the most elementary things, and I didn't have a very powerful physical intuition, and so I kind of overcompensated for becoming much more mathematical, just really leaning on the math and what we call, as you know, Michio, what we call following the chalk. And that gave me much greater confidence in the work when I could calculate from beginning to end. I could watch ideas die on the page because the math told you they were not viable. So that happened for me quite late, but when it happened, it was a kind of intense passion for this unbelievable subject that I had completely misunderstood my entire life as a student.
Now, I remember when I was a student learning physics for the first time, there were very few women in my freshman class, and every year there were fewer and fewer women. And by the time I was in grad school, there were no women at all. So did you find that intimidating, or how did you react to the fact that you were probably surrounded by physics nerds?
Well, that was uncomfortable. It was awkward. I can't say that I really understood that, and I have a kind of maybe unusual attitude towards discussing the issue of gender in science, because I feel it's something for women who go into science, it becomes this anvil around their necks that they constantly are asked, or there's pressure within the community to become a social theorist, to become a theorist on gender and science. And there are entire departments that do things like this. And they were not my department. And all of my reflections on being the only girl in the room, which went on for most of my career, were anecdotal and personal. And so I kind of ended up developing a policy that I don't discuss that, at least not publicly. I might discuss it personally. And I don't discuss it publicly because what happens is I never escape it once I do. Once I start talking about what it's like to be a woman in science, that's all anyone ever wants to talk to me about. And that I don't feel I'm a scholar in the subject. I don't have all the data, all the understanding, all of the political theory and the social theory. I just want to get out there and to talk about what I do know and what I do well, much better than that, which is physics. And when I kind of implemented that policy, which was very young, people did start asking me just about physics. And I really believe that that's allowed me to have a much bigger impact on both young girls and young boys than it would be if I merely dug into the anecdotes of my particular passage through what was, I will admit, a very difficult experience.
Okay, well, let's just jump right into your book. The book is called Black Hole Survival Guide. And you may ask yourself a simple question. How can you survive a black hole? People think that's the ultimate Roach Motel. Everything checks in, nothing checks out. But anyway,
Yeah.
let's back up a few steps. Let's say a kid comes up to you and says, could you give me a definition of a black hole? Just in a few simple sentences. How would you define a black hole?
I would say that a black hole is not an object. It's not a thing in space-time. A black hole is actually a space-time itself, and it's an empty space-time. It's one in which the curves in space-time are so strong that there becomes a point where nothing can escape, not even light. So when we discuss the black hole, what we really mean is that shadow cast on the sky by this region within which nothing is escapable.
Okay. Now, 200 years ago, we had John Mitchell, a man who said that maybe sometime in the future, we'll be able to detect a dark star, a star so massive that even light itself could not escape. So in other words, the escape velocity of a dark star would be the speed of light. However, that was 200 years ago. We didn't know anything about stars, and so it never went anywhere. So what's different now that John Mitchell didn't have? What do we know about black holes experimentally now?
Well, it was very clever what John Mitchell did, because in the Newtonian theory, when we think of light as a wave, it's a massless phenomenon and it should have no gravitational effects. But there was this trend to kind of think of light as corpuscles, as little bundles of things. And in that model, you're saying, is there a path, like when we launch some spacecraft off the Earth, where the escape velocity would ever be greater than the speed of light, and not even light could escape? And it's not that.
Oh, Jonna, we have to take a short commercial break. But after the break, we're going to continue a discussion of your book, Black Hole Survival Guide. And you are listening to Science Fantastic. Give us a call if you want to get on 100 radio stations. The number to call is 612-564-8135. Leave your name, call letter to the radio station or the city you're from, and maybe you can get on Science Fantastic. Give us a call. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Professor Jonna Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, and author of an exciting new book, Black Hole Survival Guide. And you may ask yourself a simple question: how do you survive a black hole? I thought they were supposed to gobble up everything in sight. Well, buy a copy of the book and find out. Well, headlines were made just a few years ago when astronomers announced that they had photographed a black hole at the center of a galaxy called M87. But some people scratched their heads and said, now, wait a minute. I thought black holes were black and therefore invisible. So how can you photograph something that's invisible? So did they really photograph a black hole, or something that a black hole creates, when they made that announcement, a photograph of a black hole?
Well, what they really photographed was the shadow of the black hole. So imagine taking a photograph of the shadow of a tree. It's not totally dissimilar. To have a shadow of a tree, you need light to cast the shadow. And in the case of this spectacularly huge black hole, 6 billion times the mass of the sun, 6.5 billion times the mass of the sun, in M87, what they have to their advantage is that there's material orbiting the black hole very, very, very close to the event horizon, this region beyond which not even light can escape. And so as this material is swirling around, it's actually quite hot and very bright. And imagine an orbiting disk of hot debris, kind of like Saturn's rings, but more active. It would not cast a shadow for you, except for the fact that the black hole bends the path that the light takes, so that even though this is a disk, it appears, it gives the illusion as the light emanates from the disk, it is forced on a path that bends around the black hole, both above and below. So it creates the illusion that the black hole is surrounded by light. And that little detail is what allows you to take a picture of the shadow cast by this bright material. And again, it is like taking the photograph of the shadow of a tree. So that's what we saw, and it's very close to the event horizon. We saw exactly that. We saw nothing. We saw a shadow where there could have been a bright object. And the reason we call it a black hole is not just because the shadow cast is exactly what we anticipate, it matches exactly what was predicted, but that it is so incredibly heavy, but it's only a few times the size of a solar system. And that is staggeringly small in spatial extent. And that's the trick of a black hole. It's heavy, but it's small.
Now, if you want to see the vicinity of a black hole, not the black hole itself, you can look in the direction of a constellation Sagittarius tonight. And in Sagittarius today, there is a black hole 2 to 4 million times as massive as our sun. And so then the question is, why can't you see that black hole? And does that mean also that there are black holes perhaps lurking in almost all the galaxies in the universe?
Yes, so as you said, in the direction of Sagittarius, we've named our black hole in the center of our galaxy Sagittarius A star, because that's where it is from our point of view in that direction. Sagittarius A star, as you said, is millions of times the mass of the sun, but it is less than 20 times the width of the sun across. Think of how staggeringly small that is. Taking 20 sun widths, but jamming in millions of times the mass of the sun. And so it's very small, and it's 26,000 light years away. That makes it incredibly difficult to see. The Event Horizon Telescope Project, which made this announcement, had to devise a telescope that was effectively the size of the globe by having observatories around the globe work in concert. And they liken the accomplishment to resolving a piece of fruit on the moon. That's how accurate the observation had to be to see such a tiny object so far away. And another way that they expressed it is it's like reading the date on a quarter in San Francisco from New York City. So it's actually very difficult to take pictures of black holes, and we did not, the Event Horizon Telescope has not returned a picture of Sagittarius A star because it is still difficult to observe, although they're working on it. The likelihood, you asked the second question, which is, are there these supermassive black holes in the centers of nearly all galaxies? And we believe that, yes, that's exactly the case. That means that there are hundreds of billions of supermassive black holes in our observable region of the universe.
Now, it turns out that some black holes can be the size of large stars, and some of them can wander. And some people have conjectured that there are wandering black holes in the Milky Way galaxy, in which case maybe one day we're going to be caught unawares. A black hole will sneak up behind us and basically gobble us up. So what are your thoughts about black holes the size of stars that wander? And will our sun become one of these black holes, or is our sun simply too small to become a black hole?
Our sun is definitely too small to naturally become a black hole. If some evil genius comes along and figures out a way to force our sun to collapse, our sun would only be 6 kilometers across as a black hole. It would be smaller than a city. Most black holes that form naturally by being very massive, collapsing under their own weight at the end of their life cycle, are in the tens of kilometers across range. And so they are, again, very small and very hard to detect, but what we do is this trick called microlensing. So if a black hole were to pass between our line of sight and a cluster of stars, it would make them twinkle. It would distort the image because it bends the path that the light takes to us. And so this little trick of microlensing allows us to look for black holes so that we're not caught unawares. And but there are most certainly black holes that are just freely wandering around the universe. We know, for instance, in the center of the galaxy, around that supermassive black hole, that there may be tens of thousands of smaller black holes just in wild and unpredictable orbits around that supermassive black hole. And then where we are, which is in the safer area of the galactic arms, there certainly are some that have been lost to their solar systems and have been ejected and are wandering around. The funny thing about black holes is that they're not these weapons of complete destruction that we make them out to be. They actually have to come really, really close to us to pose a problem. So if the sun were to become a black hole tomorrow, our orbit would be fine. We would not suddenly be vacuumed into that black hole. I mean, it would be apocalyptically cold and it would be dark and civilization would end, but our orbit would be just fine. So that black hole really has to be right on target to hit us, and that's just incredibly unlikely.
Okay, now you mentioned that the Earth is not going to be sucked into a black hole anytime soon. That's what kids want to know the answer to.
Yeah, but we will be eventually.
Well, we are outside the event horizon, which you've referred to a few times. So what is the event horizon? Is it the point of no return?
Yes, exactly. So the event horizon is really a region in space. So many people have heard the story. A very heavy star collapses at the end of its life cycle and begins to enter its death state. And as it collapses and gets denser and denser, there becomes a point where the escape velocity from that star exceeds the speed of light, and that marks the event horizon. Now, Sir Roger Penrose recently won the Nobel Prize just last month for the work that he did that proved that that star keeps collapsing. It cannot sit there. If you go up to this region, this event horizon, and knock, there's no surface there. There is nothing there. And I love this chapter in the book where I just am emphasizing black holes are nothing, because that star that formed it continues to fall catastrophically in the interior, and it leaves behind, like an archaeological record, an imprint on space-time of this location where, if you veer that close, the curves in space-time are so strong that you could not escape. But there's nothing there. There's no line drawn in the sand. There's no matter there anymore. The star is gone. So the event horizon is really an empty region of space-time. And that's why I refer to it as a shadow. You can only expose the event horizon if you illuminate around the black hole, and then you can see, oh, look, there's this dark shadow cast, because in this region of space-time, nothing can escape.
Okay, now kids want to know the answer to 2 questions about black holes. First, what happens when you fall into a black hole? And second, what's on the other side? Or is there another other side to a black hole? But let's take a short commercial break. And after the break, we're going to ask the question, what happens if you fall into a black hole? Welcome back to Science Fantastic with Professor Michio Kaku. With us today is John Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, author of a new book, The book is called Black Hole Survival Guide. Now, when we last left off, we were talking about, well, what happens if you fall into a black hole? This has been done, of course, by Hollywood many times, but tell us now about the physics. What happens in slow motion as you fall into a black hole?
If we only consider gravity and we ignore all of the quantum aspects of matter, the matter that actually falls in, and in fact the quantum aspects of gravity. And that story, again, going back to Sir Roger Penrose, is actually more subtle than I think people realize. When you are outside a black hole, let's say you're an astronaut in a space station safely orbiting outside the black hole, you think of the center of the black hole as a point in space. But if you're an astronaut who goes on that exploration, once you fall across the event horizon where there is nothing, there's no demarcation, there's no indication it's even happened to you, you might not even know. But once you're on the other side, it's as though space and time have switched places. And you are forced towards what we call a singularity, which is, let's say that star formed, this infinite region of the curvature of space and time, incredibly strong curvatures of space and time. You are forced towards that region inevitably. And this was something Sir Roger proved in this early paper, that it's as though space and time switch places, and the singularity is now in your future. It is totally inevitable, and so you are driven on a path towards this, and once you get closer and closer to the singularity, things become extremely unpleasant. The curvature of space-time is so strong that you feel it differently on your feet than your head. You feel your bones being crushed together because you're being crushed towards this singular point. And it's as though your body would be ripped apart and flayed. It would be a gruesome death, and it would happen very quickly, depending on the size of the black hole, so that you were dispersed into your quantum particles. You also asked an aspect that people thought about in the very early days of understanding black holes, which is, well, that singularity sounds kind of like the singularity of the Big Bang. Maybe I can sew these two kinds of space-time together smoothly. And they can be sewn together smoothly. It's not a prediction that this happens. It's just that the math allows you to do it. And in that, if you do try that, if you do speculate about that, then all of your quantum bits could be blown out into what is sometimes called a white hole, but is effectively a Big Bang. And you would, in some sense, be contributing to a new ecosystem, a new Big Bang, a new beginning, where maybe new black holes form and new planets form and new sentient life forms and emerges and asks the question. So one of the things that I think is really spectacular about that is, if you think about how small these black holes are on the outside, they can be as big as a universe on the inside. I call it like Doctor Who's TARDIS. It's like the ultimate Doctor Who's TARDIS. Here's this object that's small by astrophysical standards on the outside, but on the inside can be enormous.
Well, in 1963, there was a mathematician, Roy Kerr, who looked at Einstein's equations and assumed that the black hole was rotating so fast that centrifugal force kept it from collapsing, and it collapsed to a ring. And as you know, if you fall through the ring, you don't die. You could conceivably fall through the ring into a parallel universe. And so this does not mean a white hole necessarily, but the question is, does this mean that a wormhole can take you to another universe? Well, let's take a short commercial break. You are listening to Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us today is Jonna Levin. She is a professor of physics and astronomy at Barnard College of Columbia University, author of a new book, Black Hole Survival Guide. Well, when we last left off, we were bordering on science fiction. The question is, well, what happens if you fall through a black hole? Are you necessarily crushed to death? Some people think maybe there's a white hole that you're blown out of the other end as a new universe is creating. Other people say that, well, if you have a spinning black hole and you fall through the ring, it's not a dot at all, but it's a ring, you do not necessarily die. You can fall into a parallel universe. And if you fall in a second time and a third time, it's like going up an elevator. You simply wind up on different planes of different universes. However, this is all, of course, speculation. So tell us a little bit about where physics is leading. All these speculations about white holes, big bangs, parallel universe, What came of these ideas?
Well, so you're describing the Kerr extension, which is, it's very beautiful to draw these maps of space-time where you see them kind of one leading into the other. But I would say a much more contemporary view requires that we think about quantum phenomena. And that has led to ideas that are even more hard to wrap your head about. There are now suggestions that, let's say you fall into the black hole, it would be hard to imagine you surviving the extreme curvatures, even if there isn't a singularity. So let's just imagine you're torn to your quantum particles. There are ideas now that there are wormholes, quantum entangled wormholes, that navigate from the interior of the black hole to the exterior of the black hole. So let's say I look at one of your fundamental quantum particles inside the black hole. It actually is also outside the black hole. And that this is suggested as the source of the Hawking radiation. Hawking famously said that a black hole evaporates quantum particles that it steals from outside in the vacuum. It never comes from inside. It created this whole war between quantum mechanics and relativity. If the particles don't come from the inside of the black hole, what happened to all that stuff when the black hole evaporates and the event horizon is yanked up and there's nothing inside? And so this is one of the resolutions that says, well, actually, the stuff on the inside is the Hawking radiation, and it was navigated there through a series of entangled wormholes so that even if you are torn to shreds inside the black hole, there is a thin vapor of hope that if I cautiously reconstruct all of the information encoded in that Hawking radiation, that it will carry the details of your demise, it will carry the details of who and what you were, and that in principle, I could reconstruct from this blaze, from this explosion, especially the final radiation, I could reconstruct your experiences and who you are, and even you. So the only way you could survive that experience would be if somebody faithfully tried to reconstruct your quantum information.
Okay, well, let's jump a few steps backwards, okay, and try to break it down one at a time. First of all, Stephen Hawking said that black holes are not really black. They're gray. So tell us a little bit about what is Hawking radiation and what is the status of Hawking radiation today?
So Hawking radiation was so everything that we understood about black holes and general relativity is perfectly correct in this idealized world where we only consider gravity. And Hawking said, but that's not the world we live in. The world we live in actually has quantum particles. It has matter, and matter behaves in a quantum way. And so even though the event horizon is completely empty, it is nothing, it is nothingness, nothingness isn't actually empty all the time. And when we start thinking about quantum mechanics, we talk about the possibility that an empty region of space, can actually froth with possibility of particles popping in and out of existence. That these quantum particles create a very kind of low-level sea or froth, quantum froth in empty space. You wouldn't notice it if you fell across the event horizon. You don't notice it in your room, but it's there. And these particles must come in pairs. They have to come in pairs to neutralize each other. And what Hawking realized is in the case of this happening near a black hole, one particle can land slightly inside the event horizon and the other slightly outside. And in that way, it can permanently separate these neutralizing pairs. It can steal one and leave the other free to radiate in the universe. Okay,
Jana, we have to take another short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call. The hotline number, if you want to get on the air, is 612-564-8135. Leave your name, call letters to the radio station or the website you're listening to, and the city you're calling from, and bingo, maybe you can get on 100 radio stations that carry Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is John Levin, author of the book Black Hole Survival Guide. Now, your book talks about a survival guide. That implies that you can survive. But what does it mean to survive a black hole?
Well, a lot of the advice, I don't want to do a spoiler alert of the end of the book, but a lot of the advice also involves surviving just navigating the exploration of a black hole from the outside, avoiding the jets, for instance, if a black hole is surrounded by debris and material and magnetic fields, which it churns up into these dramatic, tight jets. Those jets are effectively astronomical ray guns. If you were to be hit by one of the jets, you would be exposed to lethal doses of X-rays and gamma rays with all of the attendant physical consequences. So the jets, in fact, we've seen jets so big that they puncture holes in other galaxies, destroying planetary systems and life in the other galaxies, if there is life in other galaxies. And so black holes can be lethal in more ways than just falling in. So I can't offer advice as to how to navigate even just the exploration. But the only way to survive falling inside would be the way that I just described, if somebody was willing to try to reconstruct all of your quantum information perfectly and reassemble you. Other than that, it is quite clear that once you cross the event horizon, your doom is sealed. So not crossing the event horizon is really the safest thing to do.
Okay. Now, some people say, now that we mentioned the concept of a wormhole, that wormholes may actually take us to the past as well as to a distant point in the universe. Stephen Hawking was jokingly said that time travel is not possible because where are the tourists from the future? And he said that the radiation that you would be exposed to would kill you. Other people have said that in a multiverse idea, radiation is not circular throughout a time machine, so you're not going to get radiated to death, that you can navigate through a wormhole to the past. But what are your thoughts? What are your thoughts about whether or not a time machine is even theoretically possible?
Well, there was a conference organized at MIT in the past for time travelers to attend. So, if you can time travel, it doesn't matter that it was in the past. You just show up when you show up. There are actual examples in straightforward general relativity, the theory of curved space-time, very artificially constructed universes where we see that you could take a path through time that closes, that comes back to the beginning. In other words, you can time travel. One example was proposed by Kurt Gödel, the brilliant mathematician, that if you had a very odd universe that was spinning in a particular way, that he proved that in that universe you could take a path and find yourself, the famous grandfather paradox, confronting your grandfather before your father was born and shooting him. So a lot of thought has gone into these possibilities, and there's some very subtle arguments. One of the problems with that idea is that we are presuming that we have some kind of free will that transcends physical reality, that is not itself bound to the laws of physics. If you find yourself on a path where you go back to confront your grandfather and you shoot him, it'll be the case possibly, for example, that he is wounded but not killed, but he's an angry man. Your father is born. He makes you an angry man, and that's why you went back and shot him. So there's a consistent narrative. It's a kind of 12 Monkeys story. And then there are other people who simply believe that there is something, a kind of cosmic censorship that will not allow these things to happen, even though technically they exist in certain models. So my feeling, I'm partial to the complicated grandfather paradox story, that whatever you do when you go back to your past has to be consistent with you being the person who goes back and does exactly that every time.
Well, it seems to me that the simplest resolution is the multiverse idea, that the river of time forks into two rivers. In your river, your grandfather lived to eventually give birth to you, but in this other timeline, your grandfather died and you no longer exist in that other timeline. So the multiverse idea would be consistent with quantum mechanics, consistent with
string theory. So you mean like a many
theory.
Worlds interpretation of quantum mechanics?
Yeah, that's right.
Yeah. That's right. So, right, in the many worlds interpretation of quantum mechanics, where you again have to invoke quantum mechanics to make sense of this, there are these sort of infinite branching, these dendritic possibilities that allow for consistent histories, and that just depends. That argument, the many worlds argument, is still very contentious, although it has many proponents. But it is, in some sense, the simplest interpretation, the cleanest, most direct interpretation of quantum mechanics. But I think what it says over and over again is singularities, the information loss paradox of Hawking radiation, time travel and the forking in the road. We can't separate quantum mechanics from gravity and understand the world. We need to understand quantum gravity to really make sense of these hard questions.
And speaking about quantum gravity, string theory is, well, what I do. And however, it's still controversial, not proven yet by any means. What are your thoughts? What about the prospect of a universally accepted quantum theory of gravity that would once and for all answer the question of what's on the other side of a black hole, what happened before the Big Bang, and questions like that? What are your thoughts about a quantum theory of gravity?
Well, I work on the consequences of string theory, and I collaborate with string theorists, even though I'm not directly in that area. And I am agnostic on string theory, but I do believe that some of the advances that we have seen are incredibly compelling. And I know that people
okay, Jana, we have to unfortunately wind up. Once again, Jana Levin is the author of a new book, Black Hole Survival Guide, appearing in your bookstores, so get a copy. And you are listening to Science Fantastic with Professor Michio Kaku. And if you want to get on 100 radio stations to ask a question, give us a call at 612-564-8135. Leave your name, call letters to the radio station, your website, and the city you're calling from. And hey, maybe you can get on national radio.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing scientific breakthroughs that are touching our lives, that are going to shape the destiny of the human race. And once again, if you want to get on Science Fantastic, if you want to be part of the fun, pick up the phone and call that magic number. Call the number 612-564-8135. Write that number down, 612-564-8135. Ask a question, make a comment, and perhaps your thoughts will be heard on national radio. Or send me email. Go to my website, mkaku.org, mkaku.org. And there's some people out there who are a little bit shy and don't want to get on national radio with your sound, but are willing to send me a question. And so I will be answering some of the emails. I will be answering some of the listener phone calls in this hour of Science Fantastic. And while you're at my website, check out some of my books. I've written 4 New York Times bestsellers. The latest one is called The Future of Humanity, The Future of the Space Program. Some people think that we're now entering the second golden age of space exploration. The first golden age, well, we won that by beating the Russians, but there was no vision. There was no guidance. There was no North Star to guide our work other than beat the Russians, beat the Russians. Well, once we beat the Russians, we realized the cost was enormous, and we gave it up. Billions of dollars wasted because we didn't have a thought-through vision for space exploration. Well, now we have Silicon Valley billionaires filling in the gap. Elon Musk of SpaceX talks about creating a multi-planet species. He says that life is simply too dangerous to put on the planet Earth. Why not have other branches of humanity in space? And the richest man on Earth, Jeff Bezos, he has a new vision, and that vision is to make the Earth into a garden. Think about that. The Earth is a celestial garden, and all the polluting industries are put into outer space. Think about that. The Earth as a celestial park. That's the vision of the richest man in the world. And these people are just not dreamers. They're putting their money, hard-earned cash, billions of dollars, invested in a new fleet of rockets without a dime from the U.S. taxpayers. You know, several months ago, the internet lines were burning up because Elon Musk launched a new rocket from Cape Canaveral. Now, you may say to yourself, ho-hum, why should I care? That rocket was seen by millions around the world. Thousands lined up the streets of Cape Canaveral to watch the launching of that rocket because it was a moon rocket. For the first time in 50 years, a new moon rocket blasted off from the very same launch pad that launched our astronauts to the moon back in 1969. Think about that. The Falcon Heavy, a Falcon Heavy rocket fully capable of going all the way around the moon with a capsule containing our astronauts. And not to be outdone, NASA has its moon rocket, the SLS booster rocket, which is going to send a capsule, the Orion capsule, around the moon sometime around December of next year. And so some people think that we are, in fact, entering a new age of space exploration. Costs are dropping. Excitement is rising. And maybe the public will realize that, hey, a new generation of rockets can take us to the moon, Mars, and beyond. In fact, that's a new presidential directive. Last December, President Donald Trump issued a presidential directive, Space Policy Directive number 1, which says our goal is the moon, then Mars, and beyond, perhaps the asteroid belt. And just think about that. NASA for 50 years has been essentially the agency to nowhere. Of course, it's sent probes to the planets. We're all grateful for that. But humans have not been beyond Earth orbit. Now, some people have seen the movie Armageddon, and they think that if we're threatened by a killer asteroid, we'll just send Bruce Willis into outer space. Wrong. The space shuttle has been phased out. In fact, the space shuttle didn't even have the power to reach deep space. We would be a sitting duck if a piece of rock from outer space was headed our direction. So think about that. Anyway, that's the subject of my latest book, The Future of Humanity, now a New York Times bestseller. And my other books include Physics of the Impossible, talking about the possibility of time travel. What does it mean if you can go backwards in time and kill yourself before you're born? Think about that. What does it mean if you could wrap time into a pretzel? Think of all the paradoxes that you could create if you could do that. Well, I talk about this and other developments in my book, Physics of the Impossible. And in The Future of the Mind, I talk about the future of the Internet. Did you know that we can now send memories on the Internet? That's right, memories. Pretty soon we'll send emotions on the Internet. Teenagers will go crazy. Instead of sending email messages with happy faces at the end of every sentence, they'll send the emotion as well. And so in other words, in this hour, we're going to take your listener phone calls and we're going to answer your emails because you can be part of the march of science. Why should we scientists have all the fun? You can be part of the fun by calling 612-564-8135. Okay, well, without further ado, let's move on to the first listener phone call.
Hey, this is Armand from Queens. I listen to you on YouTube. I was wondering how possible you think it is to go subatomic, like a person being able to shrink down to the subatomic level, like in the movie Ant-Man, because I really like that movie. Have a great day. I like your station a lot. It's awesome.
Well, thank you. And yeah, when I was a kid, there was a movie, The Incredible Shrinking Man, where a man shrunk himself and he had to fight off bugs and insects. And of course, these bugs were gigantic in size. And then you had Disney movies, Honey, I Shrunk the Kid. And we may ask ourselves a simple question. Is it possible that we can really shrink ourselves? And in fact, Matt Damon was recently in a movie where he downsized himself and the cost of living dropped dramatically because his food bill, his electricity bill, his water bill was almost nothing. So is it possible to shrink things? Well, the short answer is no. Sorry about that. And why is that? Well, first of all, what are we made of? Believe it or not, we are made out of nothing. That's right, nothing. Most of our body is a pure vacuum. And if you don't believe me, we do this experiment for our physics students. We get a piece of uranium and then put a Geiger counter behind your back, behind the uranium, and the Geiger counter registers radiation as if you're not there at all, as if you're made out of nothing, because your atoms are basically empty. That's right, your atoms are basically empty. Now, if your atoms are basically empty, so we're basically made out of nothing between the atoms and between the electrons and neutrons, protons, then why can't we shrink us? Well, the reason is quantum mechanics. It turns out that quantum mechanics set distances, like the distance to the hydrogen atom, and they cannot be changed by any known law of physics. So sorry about that. Honey, we're not going to be able to shrink the kids anytime soon. However, let's take a short commercial break.
Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to throw the lines open because it's open mic. Open mic on Science Fantastic. Here's a chance for you to get to the phones and call that number, 612-564-8135. And all we ask is that you leave your name, call letters of the radio station you're listening to, and the city you're calling from. And bingo, perhaps you can get on Science Fantastic. And also, if you're too shy to have your voice heard on national radio, you can email me a question. Go to mkaku.org, mkaku.org, and find out what I'm all about. On Facebook, we have 3 million fans on Facebook. On Twitter, we have 650,000 people on Twitter. And find out what all the excitement is about. Why should we scientists have all the fun? Why can't you have some fun too? By calling 612-564-8135. Well, the previous phone call actually raised a bunch of physics questions. He asked a question about whether or not you can shrink people, and for that matter, whether you can expand people, and what would it be like if we can somehow become Ant-Man? Well, when I was a kid, I used to love watching the movies like Them. In that movie, ants became the size of a house. They were mutated. And the question I asked myself as a kid is that possible? That an ant can become the size of a house? Or what about King Kong? Or what about the incredible 50-foot woman? These are some of the movies that I saw when I was a kid. But now I'm a physicist. And now I realize that, well, it makes for great cinema, but they're not physically possible. And in fact, the laws of physics actually change when you scale something up. For example, many people think that if an ant were the size of a house, then the ant could pick up the house. Just like ants can pick up a leaf many times bigger than its own weight. So if ants can do that, if you scale up an ant to the size of a house, then the ant would be able to pick up a house, just like in the movie Them. Well, no, it doesn't work that way. You see, if I take an animal and I double its size, so instead of being 1 foot long, it's now 2 feet long. It weighs more. How much more? It weighs 8 times more. Not just double the weight. When you scale up an animal so that it's double in size, it weighs 8 times more, not 2 times more, because you have to go by the volume. The volume we learned when we were in elementary school goes as the cube of the radius. But how much stronger is the animal by doubling its size? It's only 4 times stronger, because strength goes as the cross-sectional area of your muscles, and the cross-sectional area goes as the square of the radius. In high school, we learned that the area of a square is pi r squared, and so if you double the size of an animal, it is 8 times heavier, but only 4 times stronger. So in other words, the animal becomes weaker, proportionally speaking, as you scale it up. What am I getting to? The fact that if I take an ant and I scale it up to the size of a house, its legs will break. The ant would not be able to walk at all because the legs are spindly in size. The legs are 4 times bigger if you scale it by 2, but it weighs 8 times more. And that's why King Kong is also not possible. King Kong, instead of terrorizing New York City, its legs would break. Its legs would break as soon as it took the first step. Now, that's also the reason why figure skaters are so tiny. Have you ever met a figure skater up close? Maybe you've been to Disney on Ice or something. You realize that they are very tiny people. Why? Because the smaller you are, the stronger you get, proportionally speaking. Okay? That's why little children who are 15 years old win the gold medal in figure skating. If you're very tiny, a tiny girl, you dominate the figure skating world because you're proportionally stronger than a huge hulking guy who has all that mass, all the bones that he has to lug around. While if you're a 15-year-old girl, you fall to the floor, you just pick yourself up. Now, if you're a big hulking mass and you fall to the floor, you break your leg because your legs are not proportionally stronger. And so, in other words, King Kong is not possible. Them, that is gigantic ants, are not possible because the laws of physics are not the same when you double things in size or reduce things by half. Also, if you saw the movie Honey, I Shrunk the Kids, they shrink down to the size of an ant and they meet things like water droplets. Now, think about it for a moment. A water droplet that an ant would see looks like a hemisphere of water. That's because surface tension is also not scale invariant. Surface tension also increases when you scale things down. That's why an ant would see a drop of water as a gigantic hemisphere. And now, of course, a hemisphere of water in our world would very rapidly splash, and it would essentially be wiped out. But for a tiny ant, that's not true. For a tiny ant, a drop of water looks like a gigantic hemisphere. And if the ant were to stick its legs inside the hemisphere, it would be stuck because surface tension is also not scale invariant. And that's why sometimes when you put a little piece of sugar in liquid form on a table, ants will come because it's sugar and they'll get stuck. In fact, they'll die, stuck inside the honey-like consistency, because the laws of physics are not the same when you scale things up or scale things down. So in other words, in the movie Downsizing with Matt Damon, when you downsize a human, you find all sorts of bizarre things happening when you get smaller and smaller. If you get bigger and bigger, you get weaker and weaker. Your legs will break as soon as you try to take a walk if you're the size of King Kong. However, if you are the size of an ant, then proportionally speaking, you become Ant-Man. And Ant-Man, of course, is a superhero. So if, and this is a big if you could reduce yourself in size, you would become superhuman. But, hey, you can't do it. According to the laws of quantum mechanics, the size of an atom is fixed. Sorry about that. You cannot shrink an atom no matter how hard you try. Okay, well, let's move on now to the next listener phone call.
Hi, Professor Kaku. My name is Nahreen, and I'm calling from San Jose, California. I listen to your YouTube channel and have a question for you regarding time travel. If according to the law of physics, time traveling is possible, what if we have right now people who time travel from future, like year 3000 or 4000 to our time? They should be advanced enough to figure out how to do it, and we should have met them by now. What do you think about that? Thank you so much. Bye-bye.
Okay, well, you ask a very interesting question, the very same question that was asked by my late colleague, Stephen Hawking. Stephen Hawking said that, well, maybe time travel is not possible because where are the tourists from the future? He said that his living room should be full of tourists from the future who want to take a picture of the great scientist Stephen Hawking, but he doesn't see them. So, well, maybe time travel is not possible. And one time, as a joke, he had a party. However, he didn't invite anyone to the party. He said, tomorrow I'm going to have a party. But he didn't invite anyone because he said to himself, in the future, I'm going to invite people and they're going to have time machines and they'll go backwards in time because they know I had a party. And so he waited for people to show up from the future. Well, Nobody showed up from the future. So in other words, maybe they didn't get an invitation in the future to go backwards in time to meet Stephen Hawking. So you ask a very interesting question. Where are the future people? Well, there's several ways of analyzing this question. The simplest way is to say that time travel is not possible, but that's too easy because Einstein's equations do allow for time travel. Einstein said that time is a river, but the river of time can have whirlpools, and the river of time can fork into two rivers, in which case you can actually go backwards in time. Einstein himself realized that. Well, let's take another short commercial break, and after the break, I'll talk about, well, why don't people from the future visit us if they're that advanced and they have time machines? We'll answer that question in a moment. But you are listening to Science Fantastic with Professor Michio Kaku. Give us a call. Welcome back to Science Fantastic with Professor Michio Kaku. Give us a call. The hotline number is 612-564-8135. You're not going to get a busy signal. You get right to us if you call 612-564-8135 and leave your name, the call letters of the radio station you're listening to, and the city you're calling from. And hey, maybe your thoughts will be heard on national radio. Well, before the break, we had a question, a very profound question that my colleague Stephen Hawking asked himself many times, and that is, where are the people from the future? If time travel is possible, maybe not today, but if time travel is possible in the future, then perhaps our descendants will have gone backwards in time to visit their illustrious ancestors, i.e. us, and they should be taking pictures of us. They should be shaking our hands. So why not time travel? Well, ever since Stephen Hawking made that comment years ago, many scientists have come up with their own private theories. One possibility is that maybe they have visited us, except after visiting us, they realize that we're a bunch of fools in the past with nothing to offer them, and they just get bored. I mean, let's say you have a time machine, and you go back to watch the dinosaurs. But after watching the dinosaurs have lunch a few million times, you get bored. I mean, they don't talk back to you. You can't have an interesting conversation with a dinosaur. It's the same old dumb dinosaur having breakfast. And you say to yourself, I'm not learning anything. This is not exciting. So maybe time travelers from the future have already visited us, but they simply said to themselves, humans are not worth visiting again. I mean, after all, if they went backwards in time and watched television and witnessed the Cardassians, they would be convinced there's no intelligent life on the Earth. Nope, next planet. So that's one possibility. Another possibility is that maybe they do come back to the past, but they're invisible. Invisibility is one thing I write about in my book, The Physics of the Impossible. Yes, it is possible to make something invisible. We can't do it yet, but we can make things invisible under microwave radiation, not visible light. But the Pentagon is funding this research. So in the future, maybe we'll have time machines maybe we'll have invisibility centuries before we have time travel. And so it means that maybe we are visited. Maybe there are people taking our picture, tourists from the future, but they are invisible. And that's why we can't see them. Well, there's yet another way to resolve this paradox, and that is if you could invent a time machine by creating a wormhole, it turns out that the wormhole would connect 2 points of the present. Therefore, even if you were to separate these 2 points, you cannot go backwards in time earlier than when you built the machine. That's another possibility, and that is that, yes, you can build time machines, but you cannot go earlier than the time at which you created the time machine. That objection has been... Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. You're not going to get a busy signal. Give us a call. The number to call is 612 564-8135. And maybe you can get on national radio with your question or comment about science. Well, before the break, we had a question, a very interesting one, about time travel. And it turns out that, yes, Einstein himself realized that general relativity allows for time travel under certain circumstances. First of all, if I have a spinning object, if the universe itself were spinning, or I have a gigantic cylinder that's spinning rapidly, a spinning pole, and if you were to go around the pole or around the universe, you would go backwards in time. Another class of time travel solutions are black holes. If you could go through a black hole and stabilize it with something called negative energy, then you can open a gateway to the past and keep it stable so that you're not going to get crushed by the wormhole. That is another classification of time travel. And then the question is, well, if time travel is allowed by Einstein, then why don't we have it? Why don't we have visitors from the future? Well, let me say a few things about visitors from the future, because there are paradoxes that you encounter. Now, the mother of all paradoxes, the greatest paradox of all, was given to us by science fiction writer Robert Heinlein. And let me summarize that logic. Many, many years ago, there was a young girl that was left as a baby on the doorstep of an orphanage. The nuns picked up the baby. They didn't know where she came from, what her name was, so they called her Jane. And poor Jane grew up without knowing who her mother was or who her father was. Well, when Jane became a teenager, she became a beautiful young woman, and she got a boyfriend. But it's a sad story. She gets pregnant, and her boyfriend disappears into the darkness, never to be seen again, and she's left pregnant at the hospital. Poor Jane doesn't know who her family is, left as an orphan. Now she's pregnant, no boyfriend, and it's even worse than that. The doctors at the hospital find out that Jane is a hermaphrodite. She has both sex organs. So she's bleeding, and she has to be saved. So the doctors do an emergency operation and change Jane into Jim. Well, Jim wakes up with this huge headache, realizing, oh my God. First, she was an orphan, left as an orphan on an orphanage steps, and then got a boyfriend, but then he dumped her, and now she's abandoned, pregnant, and then that night, somebody steals her baby girl. What a disaster. Everything went wrong. Well, poor Jim grows up to be a barroom drunk. Anytime someone challenges him and says, who are you, Jim? Are you really Jane? Where'd you come from anyway? Who's your mother, your father? Well, now poor Jim is once again dead drunk on the bottom of a bar, and a bartender comes up to him. And a friendly bartender says, Jim, wake up. I'm really a time traveler. Come into my machine, and we will unravel the mystery of who Jane/Jim really is. And so they go back into the past, and poor Jim is left somewhere in the past. He's dazed, doesn't know where he is. But then he meets this beautiful 17-year-old girl, and it's love at first sight. But it was not meant to be. They quarrel, and Jim stomps off into the darkness. But then he finds out that his girlfriend is pregnant. And Jim says to himself, oh my God, this happened to me when I was a young girl. I'm going to go back and make things right. So Jim goes back to the hospital, steals his own baby girl, goes back into the time machine, and then drops the baby girl off at an orphanage. And at the steps of an orphanage, the next day, the nuns find this baby girl. They don't know what to call her, so they call her Jane. And Jane grows up wondering, who's my mother? Who's my father? Well, meanwhile, Jim says to himself, I can't be a barroom drunk all my life. I got to get my act together. So Jim decides to join the Time Traveler's Corps. And he has many exploits in the annals of time. And now Jim is an old man. He's an old man now. And he says to himself, I want one last mission in time. I'm going to go backwards in time and impersonate a bartender to meet a certain barroom drunk who just got into a fist fight because someone said, who are you, Jane/Jim? Where'd you come from? Who is your mother, your father? Now, for 10 points, here's the question for you. Who is Jane's mother, father, brother, sister, and uncle? I'll give you the answer after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Give us a call if you want to be part of the fun. Give us a call at 612-564-8135. And all we ask of you is that when you hear the recording, leave your name, call letters of the radio station if you're listening to one, and the city you're calling from, and make that question, make that comment, and perhaps you can get on Science Fantastic. Well, before the break, we had a very interesting call from a listener who asked about time travel and what happens if you meet someone from the future. Well, as I mentioned, perhaps the greatest of all paradoxes in time travel was given to us by Robert Heinlein in a short story. And in this short story, we start off with a young baby girl called Jane, grows up in an orphanage, not knowing who her parents are. And as a teenager, she meets a handsome stranger but gets pregnant, and she's abandoned. The baby girl is born at a hospital, but someone steals her baby girl. Well, poor Jane, she's left without a family, now without her baby daughter, but the doctors realize that she's dying. They have to change Jane into Jim, a sex change operation. And Jim becomes a barroom drunk who one day finally meets a bartender, a time traveler who says, I will unravel the secret of Jane. They go backwards into the past, and Jim meets this beautiful teenage girl, and it's love at first sight, and he gets her pregnant, but he says to himself, I got to take responsibility. I cannot let history repeat itself. So he kidnaps his own baby girl and goes backwards in time once again, and drops off the baby girl at an orphanage where she becomes Jane. Now, here's the question. Who is Jane's mother, father, brother, sister, daughter, aunt, uncle? Jane is a family tree unto herself. Now, can you imagine a family get-together? A family get-together and they get into a food fight, and someone says, you did this to me. No, you did that to yourself. Think about it. Is that possible? Well, if time travel is possible, you can be your own mother, your own father, your own grandfather, your own granddaughter. You can be a family tree unto yourself. So, is that physically possible? Well, yes and no. You see, Stephen Hawking finally concluded that time travel is not possible because the machine would explode when you went into the time machine. Time machines are allowed under Einstein's equations, but quantum corrections build up. And they build up to the point where the machine explodes, therefore you cannot go backwards in time. Well, I've looked at that calculation by my colleague Stephen Hawking, and I realized I think he made a mistake. He made a mistake because in quantum mechanics, if you were to go backwards in time, the timeline splits in half. Because time is constantly splitting into a multiverse of quantum universes. Therefore, when you go backwards in time to meet Jane, you meet someone else who looks like Jane, but is not really your Jane. Genetically equivalent, has the same memories as Jane, but is Jane in a different timeline. Now, I saw the movie Back to the Future Part 2, and Doc Brown goes to the blackboard and he draws a long parallel line, a long line, and says on the left is the past, on the right is the future, and here's the timeline. And then he drew a fork in the timeline. And he says that's what happens when you go backwards in time. The timeline splits and a parallel universe opens up. So in other words, instead of having one universe with many copies of Jane, no, you have many universes. In each universe, there is its own copy of Jane. Now, this, of course, raises philosophical questions. It means, first of all, that if the multiverse theory is really possible, there exists another universe where you are not alive, or you turn out to be a serial killer, or you turn out to be some kind of degenerate, or you turn out to be the richest man in the world. Think about that. Waking up one day and finding out that you're in the wrong universe and that you are the richest man in the world or the deadliest serial killer of all time. I mean, you go berserk thinking about these things. And I, as a physicist, had to think about these things professionally because at the atomic level, that happens all the time. At the atomic level, yes, electrons are constantly splitting apart. And that's why we have television. That's why we have radio. That's why we have transistors. That's why we have lasers. The wonders of the modern age can all be traced back to electrons being more than one place at any given time. Now, if you get a headache thinking about these things, you're not the only one. I've been at conferences where Nobel Prize winners bump into each other and they argue about this. 50 years after Einstein and Bohr struggled with these questions, we're still struggling with these questions. And to me, the simplest way to get around all these paradoxes is to assume that the universe splits every time a quantum decision has to be made. There are no paradoxes in time travel. If you go backwards in time, you've entered another universe, not your own past, somebody else's past. Okay, well, let's move on now to the next listener phone call.
Hello, this is Frank in Columbus, Ohio. And my question is about Jupiter. Is it possible that at some point in the far future, Jupiter could accrete enough mass to become a brown dwarf? Currently, it's only about 1% of the mass required for a brown dwarf, but possibly as the sun becomes a red giant and starts to shed off its outer layers, could it at some point...
let me answer that question really quick. The answer is no. In order to ignite to become a star, you have to satisfy what is called Lawson's criterion. And as you pointed out yourself, Jupiter is way too small to satisfy Lawson's criterion to create another star. So our sun will be alone in our solar system. We're not going to live in a double star system, even though science fiction writers love that idea. But once again, you've been listening to Science Fantastic. Give us a call. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Well, in this hour, once again, we're going to throw the lines open because it's open mic on Science Fantastic. That's right. This is the chance when you can talk back to the radio. You can talk back to the internet. So give us a call. The hotline number is 612-564-8135. Write that number down, 612-564-8135. 8135. You'll get a recording. Leave your name, call letters of the radio station you're listening to, and the city you're calling from, and bingo, perhaps you can get on national radio on Science Fantastic. And also, if you want to send me email, if you're too shy to have your voice heard on national radio, you can send me email. Email address is mkaku.org, mkaku.org, and it lists many of my books, including my 4 New York Times bestsellers. The Future of the Mind talks about the future of science when we probe the living brain, telepathy, telekinesis, recording dreams. Believe it or not, we can do all of the above. In Physics of the Impossible, I go 500 years into the future. Well, we might have starships, teleportation, maybe even time travel. And in Physics of the Future, I talk about the next 100 years, robots, artificial intelligence, cancer research, transportation, space travel. And then my latest New York Times bestseller is The Future of Humanity, where I talk about going back to the moon, going to Mars and beyond. What does it mean to have a starship? What does it mean if one day we can encounter a civilization in outer space? What would it be like to meet alien life in outer space, an alien civilization perhaps more advanced than our civilization? Well, all these things are talked about in my books. Go to mkaku.org to find more and give us a call. 612-564-8135 is the number to call, and you can get on Science Fantastic. And maybe I'll be coming to a city next to you, signing your copy of The Future of Humanity. And by the way, afterwards, after I sign your book, you can go to eBay and auction it off for money. That's right. You can actually make money coming to one of my autograph sessions because autograph books actually sell for a lot of money. Okay, well, like I said before, the lines are open. Give us a call, 612-564-8135. So let's take the first listener phone call.
John Thibodeau, Baton Rouge, Louisiana. Don't have the call letters. Can a black hole actually be just a rip in time? And that's what we're seeing, time distorted? Thank you.
Well, you're absolutely right. We think that a black hole is in some sense a rip in time. So let me explain. Let's say I have a trampoline net and I put a shot put in the middle of the trampoline net. The trampoline net does not rip, but of course the ball descends and sinks into the trampoline net. And then if I get a marble and I fling the marble around the shot put, it'll orbit. It'll actually orbit around the shot put. Now, that marble is actually the Earth, and that shot put is the sun, and the trampoline net is empty space. So we have another way of looking at why the Earth goes around the sun. Why does the Earth go around the sun? Not because gravity pulls on the Earth. That's what Newton would say. Einstein would say, no. Space pushes. That's why we go around the sun. And why are you sitting in your chair today? You're sitting in your chair not because gravity is pulling you down into the chair. No. You're sitting in your chair today because the space above your head is pushing you down into the chair. And so this is a completely new way of looking at space and time. So if you want to summarize Einstein's general theory of relativity in one simple phrase, it is that gravity does not pull, space pushes. And then the question is, what happens if the shot put gets so heavy that it actually begins to tear the fabric of space and time? And that's what a black hole is. It is a rip in the fabric of time. But then the next question is, well, what happens afterwards? What happens if you throw a marble into the black hole itself, into the rip? Where does the marble go? Well, the short answer is we don't know. Now, we see black holes at the center of galaxies throughout the universe. If you want to see a black hole tonight, go outside in the night sky and look in the direction of the constellation Sagittarius. And in the area Sagittarius A, there is a raging black hole. Now, why can't you see it? Well, first of all, it's in the middle of a galactic nuclei, a cluster of stars that looks like a fireball. By rights, you should see a fireball brighter than the moon. A fireball brighter than the moon coming out every night. But you don't see it. Why? Dust clouds, galactic dust. It turns out that the galaxy, the Milky Way galaxy, is quite dusty. In fact, that's where we come from. We are made out of galactic dust. But that's also the reason why you cannot see the center of the galaxy, and that's why you cannot see this fireball that rises every night, but you can't see it because of dust. Well, at the center of the fireball, there is a black hole. It weighs 2 to 3 million times the mass of our sun, so we know it's there. And we've even had pictures of stars being eaten up by this black hole. And perhaps maybe next year, we'll have photographs of the center of this black hole. Surrounding the black hole, there's a sphere. The sphere is called the event horizon. It is the point of no return. If you fall into the sphere, you are going to be inevitably crushed at the center of a black hole. How? We don't really know. But we're lashing together several radio telescopes around the world to gain the resolution of a gigantic radio telescope the size of the Earth. Now, to build a radio telescope the size of the Earth is impossible. It would cost too much money. But by lashing together several smaller radio telescopes scattered around the surface of the Earth, and then combining the signal in a computer, we can recreate the image as seen by a radio telescope the size of the planet Earth. That telescope is so powerful that it can actually zero in on the event horizon. This is amazing. I never thought that in my lifetime I would be able to talk about photographing the event horizon of a black hole. That is the point of no return, a sphere that surrounds the black hole. We're going to have pictures of this perhaps as early as next year. Amazing, truly amazing. And then the big question is, what happens if you fall into the event horizon? Well, as I said before, we don't really know the answer. However, there's a Nobel Prize waiting for the enterprising scientist who figures out what lurks at the center of the event horizon. One possibility is that it's really a ring, not a dot, but a ring that rotates very fast, so fast it prevents you from falling through. So anyway, let me take a short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. Keep the calls coming because the number to call is 612-564-8135. Leave your name, call letters of the radio station you're listening to or the internet, and the city you're calling from, and perhaps you can ask your question on national radio. Or if you're too shy, send me an email and write the question down, and we'll answer it on the air. The web address is mkaku.org. Well, before the break, we had a quick question about, does a black hole rip the fabric of space and time? The answer is yes, but how does it rip the fabric of space and time is still being debated by physicists today. All we can say is that surrounding a black hole, there's a sphere called the event horizon, and inside the sphere, perhaps there is a ring being the remnant of a rotating black hole. It collapses to not a ring, not a dot, but a ring. And if you fall through the ring, perhaps you fall through a gateway to another universe. That is still not verified. However, we see these black holes in outer space. You can see one tonight in the constellation Sagittarius. They're everywhere we see galaxies. Black holes working in the hearts of galaxies. Okay, let's move on to the next listener phone call.
Hello, my name is Robert Carretero. I'm calling from Miami, Florida. Listening to you on the internet. And my question is, now that NASA has discovered organic complex molecules on Mars and also methane, what steps are they going to be taking to see if they find some fossils or, determine how long ago life existed on Mars? Thank you.
Well, I was on the Fox channel being interviewed even before NASA made its announcement of organic chemicals found on Mars. And I was asked to make a prediction. What will NASA find with its Curiosity rover on the surface of Mars? And I said that, well, I hate to be a party pooper, but we're not going to find evidence of little green men. We're not going to find evidence of life, but we will find evidence of the precursors of life. Organic carbon-based molecules. Organic molecules that will one day, if Mars had continued on its track, one day create perhaps the first DNA molecule. However, we didn't go that far. In other words, about 3.5 billion years ago, Mars lost its oceans. It lost its riverbeds, and it became a dead planet. Why? We're not sure, but we think that the solar wind blew the atmosphere of Mars away. Mars has no magnetic field to speak of to protect it. As a consequence, the solar wind blew much of the atmosphere into outer space and therefore lost most of its water in the process. So, are we going to find fossils? I don't think so. Are we going to find shells and skeletons? No, I don't think so. But will we find amino acids? And that, I think the answer is yes. When you crack open meteorites from outer space that landed on the Earth, many times you find amino acids. Amino acids are the precursors of proteins. You stack a bunch of amino acids together and it creates proteins, and that's what we're made out of. For the most part, we are made out of proteins. So that's the next step. The next step is to keep on drilling into the Martian rock to find evidence of amino acids, perhaps maybe even a DNA molecule. That would be a real game changer. But to find life as we know it, I tend to doubt it. Mars is bleached by the sun. For all we can tell, it is a dead planet. However, we're now digging underground into the soil of Mars, and so maybe we'll find some surprises, maybe evidence of ancient microbial life. That, I think, is the maximum we can expect. We're not going to find little green men, but we may find evidence of ancient microbial life on Mars. Okay, well, let's move on to the next listener phone call.
My name is Madison Wolf. I'm from Yorkville, Ohio. And my question is, if time travel was possible given Einstein's equations, and, the details and workings behind that. Thank you.
Yes, Einstein proposed his general theory of relativity in 1915. And then around 1949, he was at Princeton, and his next-door neighbor there was Kurt Gödel, one of the greatest mathematicians of the century, in fact. And what Professor Gödel found was a new solution of Einstein's equation, which allowed for time travel. He assumed that the universe was rotating, and if the universe was rotating and you went around the universe, you would come back before you left. In other words, you would become a time traveler going backwards in time. Now, Einstein knew about this because, of course, that was his next-door neighbor at Princeton, and he was very disturbed. Einstein himself thought that his equations might allow for time travel, but he couldn't quite get himself to believe that was real. So in his memoirs, Einstein wrote that, quote, "We can dismiss these time travel solutions because they're not physical." In other words, the universe expands. We have a big bang, not a big swirl. We have a big bang. And the universe expands uniformly, doesn't rotate. But if it did rotate, then perhaps you could journey back into the past whenever you wanted. So in some sense, thank goodness we don't live in a rotating universe, because then all sorts of paradoxes could be formed. But then in 1963, Roy Kerr, a New Zealand mathematician, discovered another solution of Einstein's equation, which was even crazier than the Gödel solution. He found that black holes, that we mentioned before, rotate. Rotating black holes do not collapse to a dot, they collapse to a ring. If you fall through the ring, you wind up through a wormhole, which can also be a gateway into the past. Since then, we've discovered scores of solutions which allow for Einstein's equations to give us time travel. In fact, there are so many solutions that Stephen Hawking tried to catalog them. The late Stephen Hawking found a whole classification of time travel solutions in Einstein's equation, and he found a commonality between all of them. It turns out that what you need to create a time travel solution is negative energy. Energy that is less than zero. We don't see negative energy too often, but in the laboratory, we can actually make negative energy. That's the common factor among all these time travel solutions that Einstein found, negative energy. Now, negative energy would make possible not just time travel, but warp drive as well. Now, in Star Trek, the Starship Enterprise, the crew there, tries to find dilithium crystals. Dilithium crystals are the engine that makes the warp drive possible and maybe even time travel. But of course, dilithium crystals don't exist. That was a figment of the imagination of Gene Roddenberry, the creator of Star Trek. But in the physics laboratory, yes, we have a counterpart of dilithium crystals called negative energy. However, what's the catch? There's always a catch someplace. You need fabulous amounts of negative energy to stabilize a black hole. First of all, you need a black hole to open a gateway through space and time. But the gateway is not stable. Then you need negative energy to stabilize the gateway so it doesn't collapse on itself. So here we are, Today, we realize that there are scores of solutions of Einstein's equations which allow for time travel. And according to Stephen Hawking, the commonality is that you need negative energy to keep the gateway open to the past so that you don't get crushed by the black hole as you enter the gateway. So, what does that mean for us? In the short term, nothing. Because the energy necessary to open up the gateway is that of a black hole, and don't expect anyone to play with a black hole anytime soon. This is really for a very advanced civilization, perhaps a Type 3 civilization, a civilization that has galactic power, that could, therefore, use Einstein's equations to go into the past. That is something we cannot rule out. Okay, well, let's move on to the next listener phone call.
Hey, this is Brandon from Manhattan, and I was wondering, do you believe that it's possible that cannabis kills cancer cells? I know that there's thousands of cancers, that's what you said, but you think it's possible that cannabis can slow down or even kill cancer cells? Thank you very much.
Okay, well, let's take a short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. If you want to be part of the fun, then pick up your phone and give us a call at 612-564-8135. And some people say to themselves, come on, I don't want to get on national TV, or national radio, because I'll look like a fool. I'll ask some dumb question and everyone's going to laugh at me. Well, just remember that sometimes the dumb questions are the most profound questions of all. Therefore, ask away. And chances are, if you have that dumb question, chances are hundreds of other people have that very same dumb question, but are too embarrassed to ask on national radio. Well, don't feel embarrassed calling me on national radio. The number to call is 612-564-8135, because sometimes the dumbest questions are the most profound questions of all. Years ago, there was a 23-year-old gentleman who asked himself a simple question. Does the moon fall? Such a simple question. Does the moon fall? He saw an apple fall, and he said to himself, well, apples fall because they're attracted to the earth. Why doesn't the moon fall? Because it's also attracted to the earth. Well, one day he saw an apple fall, and then he asked himself a stupid, dumb question. If an apple falls, does the moon also fall? He was the first person in human history to ask that simple question. Does the moon also fall? Well, he tried to calculate the mathematics of the falling moon, but he couldn't. So he had to create his own mathematics. That mathematics he created is called calculus. The theory that he came up with is called the theory of gravity. And who was this 23-year-old gentleman? His name was Isaac Newton. So by asking a children's question that seems preposterous, he came up with a theory that made possible not just a theory of gravity, but mechanics as well. And that mechanics made it possible to create machines. Machines where we can actually calculate the stresses and forces on every part of the machine. And that gave us the Industrial Revolution, one of the greatest revolutions in all of human history. The revolution of machines was, in some sense, initiated by a young gentleman who asked himself a dumb question. Does the moon also fall? Well, once again, you're listening to Science Fantastic, and let's move on to the first listener phone call.
Hi, this is Vlad. I'm calling you from San Francisco. I have a question on the specificity around mankind's ability to pull out of the climate crisis and growth as it pertains to carbon emissions and rapid polar caps melting. Thank you.